Hey, welcome back. So now we're going to do testing for the quality of K-population means in observational study. In the previous video, we took a look at the difference between an observational study and an experimental study, and we also reinforced factor treatment, experimental units, response unit. And we saw this diagram here, and we saw this right here. And and the terminology of all of that. And it's really good to familiarize yourself with the terminology, factor, treatment, experimental units, completely randomized design, and that diagram, and then an example of that here, and an example of that here. So this was an experimental, this was an experimental study, And then we also had an observational study, which was this one right here. And this is the one we're going to solve in this video. And I'm deleting that because I also have it down here, and I just put it up there when we were working in the previous video for reference. And so that observational study is right here, and where we're going to end up is right here. So this is something we've already become familiar with, and we've done it quite a bit now in the course. And so this is where this is all going to end up. And we're looking to see if the population means for Atlanta, Dallas, and Seattle, if they're equal, which would mean that they all have the same population mean, right? They're all equal. And that would be this situation right here. The null hypothesis is true, right? The samples, right, are inferences for the population mean. So this sample is an inference for this population mean, this one's for this population mean, and this one's for this population mean. And if they're all equal, that means they're all the same population mean, and they're all using the same probability distribution. And if this null hypothesis is not true, then those samples are actually inferences for the population mean. And those population means, at least two of them are not equal, which means they have different probability distributions, and they have a different population mean, mu. Right? That's mu, the population mean, that Greek symbol right there. So it means they have different probability distributions. And we could start to say that there's a difference between, like if it's our experimental study, there's a difference between assembly, how many items get assembled each week. Or we could say there's a difference between the test scores, that if these are the three plants, the three plants have different population means for what the test score is. And we're using our sample to make inferences about the population. And so that problem that we're going to do, right, is going to end us up, I'm just looking for where is the end of that. It's going to end us up right here. And what we're going to see is we're going to reject the null hypothesis. So the samples that we get will make inferences about the population means. So the sample means that we get will make inferences about the population means. And we'll do that for Atlanta, we'll do that for Dallas's population mean, we'll do that for Seattle's population mean. The samples will make inferences about those. And what we're going to be able to say with 95% confidence, that'll be our confidence level, our confidence coefficient, is that we're rejecting the null hypothesis. That means that at least two of these are not equal, right? They have different population means. And employees at different sites, whether it's Atlanta, Dallas, or Seattle, have different levels of awareness about quality, right? So it's a quality awareness examination, and there's different levels of awareness of quality at the different places. So this is our first, we're going to we select 6 employees from each plant. And so at each plant, 1, 2, 3, 4, 5, 6, we have, the test scores from 6 employees. And there are the 6 employees from Dallas, there are the 6 employees from Seattle, and there are the 6 employees from Atlanta. And then we have a sample mean, and then we have sample variance, and then we also have the sample standard deviation. And just because you're most likely new to statistics, we have, do I have it? I'm going to go get it. Hang on one second. Here it is. We have this diagram right here, these notes right here, and here's how we would calculate the variance. And so I'm just going to not make that so big. I'm going to make it smaller if I can. We'll see if Microsoft allows me to do that. And there's no perfect computer. Some are better than others. And and so here is like to calculate the variance, we would take each individual data point. So if we were doing it for this one, we'd take each individual data point, and then we would subtract it from the mean, right? So we would subtract the mean from it, and then we'd square that, and then we'd add all those differences up. So each data point minus the mean, 85 minus 79, 75 minus 79, 82 minus 89, 76 minus, 82 minus 79, 76 minus 79, 71 minus 79, 85 minus 79. I think I could like be one of those people that works at the auctions. Do I hear 85? Do I hear 85? Do I hear 79? So here's, and then we get all those differences. We square each one, we add them up, and we divide by n minus 1, which would be 6 minus 1. So it'll be divided by 5, and that will give us our sample variance. And then we take the square root of that, and we get our standard deviation, because standard deviation is the square root of the variance. And so that's how we would calculate that table there. So when I dump all this in, I guess, first of all, yeah, I guess we'll look at the ChatGPT explanation, but then there's going to be something that is going to be adjusted about that. So let's go through this example. The goal is to determine whether there's significant difference. And I really like the way ChatGPT explains things. And so, to get this explanation from ChatGPT, you could just upload this slide right here. You could go to File, Download, PNG, download the PNG, upload it to ChatGPT, make sure that you're using the 4.0 version. It's going to give you better results. That's the paid version. So whatever the newest version is, at the time you're watching this video, use the newest, latest, greatest. You're going to have to pay for it, but it'll give you better results. And you want to do that because the results are pretty good. They're really great, actually, but they're not perfect. And sometimes you have to have conversations with ChatGPT like you would a person to try to determine what is the best outcome, or to clarify points that aren't clear for you. So anyhow, you upload this slide, and then you just say, hey, can you please solve and explain this problem to me? And it'll produce output like this, right? And so that's what we're going to see right now. And so the goal is to determine, and it's insightful to see how it thinks about it, because ChatGPT was trained on all of the information that's available online plus more. And so it's really a synthesis of like how people talk about statistics and all the information out there about statistics. And so it really provides you with like the best way to kind of talk about statistics and think about things. So the goal is to determine whether there's a significant difference in the mean scores of employees at 3 different plants, Atlanta, Dallas, and Seattle. Like that sentence right there is gold. It's golden for this problem. Determine whether there's a significant difference. And the fact that significant is in there, right, is an important word. Like 95% level of confidence, right? Confidence level, confidence coefficient. Like we have a level of significance. Literally, it's 0.05 is our level of significance, right? And so what does it mean to be significant, right? To what degree? And so we want to determine whether there's a significant difference in the mean scores of employees at 3 different plants. We will use analysis of variance, ANOVA, to see if the means of the examination scores for the 3 plants differ significantly. So analysis of variance is good for testing, right, equality of means when you have 3 or more means. So first we're going to define our null hypothesis, and when we define a null hypothesis, again, our little sort of heuristic, our rule of thumb is this right here. So I'm just going to copy that and bring it down here, and we'll paste it right there. And the null hypothesis is the area where we put equality, but it's also the status quo, the current state. Nothing has changed. There's been no change. So we're just going to start out with the assumption, well, first of all, we want equality in the null hypothesis, so we have that there. And then we also are just going to have the assumption that right now, the current state of things is that the knowledge of quality awareness in all 3 plant locations is the same. And then the alternative hypothesis is at least one of the plant's mean examination scores is different from the others. Like that's beautifully worded. And like I've become well acquainted with how in statistics, things aren't talked about clearly, and partly I think it's just because it's not a natural, normal way for humans to just think, and it's also partly because they build a framework for thinking about all kinds of different problems, so you do need some intellectual structure to sort of put problems into some framework where you have different words and terminology and ways to do things. But also, so it's a little bit not a natural, normal thing. And then also you have new terminology and structure and frameworks for thinking about different problems. But I found that like a lot of statistics explains things in a way which isn't really all that clear. And this is great, right? This explanation right here for this alternative hypothesis, at least one of the plant's mean examination scores is different from the others. It's a great explanation. So then we go to the next step where the data provided are the examination scores for 6 employees at each plant. And so we could grab this and we could just kind of check. And did ChatGPT do its job right? And you want to be, you want to have healthy skepticism in life. In life, you want to have healthy skepticism, right? Which means that you aren't a nihilist. And a nihilist is somebody who is against all institutions. Let's see what it actually means. A person who believes that life is meaningless and rejects all religious and moral principles. It's impossible to argue against a nihilist.
Nihilist.
Nihilist. Nihilist. I'm so glad they have this because I'm learning how to pronounce different words right along with you.
Nihilist.
Nihilist. So you don't want to be, that person who just rejects everything just to reject it. But it's also good to have healthy skepticism. And I'm just going to make this smaller. And healthy skepticism will keep you safe in life, right? Like you want to try and see for yourself. You don't just believe something because it's written down somewhere, because somebody said it, or because it's printed in a book, or because I said it. You go and see for yourself. You try and see for yourself. You think. You use your brain, right? You're given a brain for a reason. So anyhow, all of that's to say we're going to check the data here. And you can just see 85, 71, 59, and then we have 67, 62, 67, 82, 85. My glasses are on top of my head, not on my face. But I got to move closer like that to really kind of see it. So I'm just kind of in a weird space on this computer. I'm almost far enough away to see it okay, but then I have to get closer if I use my glasses. So then the sample means are 79, 74, 66, and the Atlanta variance 34, 20, 32, 34, 20, 32. So that's all cool, right? So there's the data overview. And then we're going to do this step 3. Perform ANOVA, we need to calculate the 3 key components. The sum of squares for treatment, the sum of squares for error, and the total sum of squares. And then calculate the overall mean, right, of all observations combined, 79, 74, 66, 79, 74, 66. Add those up, divide by 3, we get the overall mean of 73. And again, to calculate the sum of squares treatment, SSTR, SSE, and SST, we could come up here, and I'm going to grab this slide here. It's now one of our terminology slides. I'm going to grab it, and I'm just going to bring it down here so we have close and easy access to it so that we can reference it. And I'm going to put it just right there. And so here, again, is SSTR, SSE, and then SST is right down here. And it's the total sum of squares. And so there's different formulas here. So this is the formula provided by the textbook, and this is the formula provided by the textbook. But we're going to see that ChatGPT offers another formula, a different formula for the sum of square errors, and that leads to discrepancy. So in the previous problem, for whatever reason, that didn't create a discrepancy, but in this problem it does create a discrepancy. And I don't have a solution for that. So if you want to, if you do have a solution, let me know. And I'd love to hear. I did some thinking about it, but I didn't readily find a solution. And I asked ChatGPT about it, and it didn't really come up with an answer that provided an explanation other than, there's a simplified approach and a more complex approach, and the textbook's using the more thorough, complex approach. So that's it. But in the previous example, there was no discrepancy, even though they had different formulas, and this one is. So and then you calculate your sum of squares for treatments, and you get that, 516. And so this is the more simplified version that ChatGPT is using. You do your SSE and the more simplified version that ChatGPT is using. And this is the one that's going to differ from what was provided by the publisher, the textbook, and this presentation. And so here's a little information on that. And, we'll look at that. We'll see it. And so then you get your degrees of freedom, calculate your degrees of freedom. And so you do that for treatments. And you also do that for your error, and treatments will be in the numerator because SSTR feeds into MSTR, which goes in the numerator of your F test statistic. And then SSE goes into the denominator. of your F-test statistic. I have to slow down, like going over speed bumps when I say that. And then you get some value, right? So this is your degrees of freedom for treatments for the numerator, degrees of freedom of error for your denominator. And treatments versus error, treatments is between, right? Between the treatments. That's why it's treatments, right? These are the different treatments, the different plants, or these are the different treatments, the different assembly methods. And so we have, treatments like looking at what is the MSTR. It's the mean square due to treatments, or the between treatments estimate of variance. So we're looking at the difference between the mean of each treatment and the overall mean of all of the data, right? And so between treatments, MSTR, SSTR, that's like between the data values. And so between the data values, we'd be looking at the difference between this mean and the overall mean, this mean and the overall mean, this mean and the overall mean. And so it's this mean of each treatment and the overall mean, which is in our textbook, the notation is a double bar over X. It's the mean of means. And so anyhow, the point I want to make is that treatments is for between, MSTR, SSTR, mean square due to treatments, between treatments estimate of variance, or MSTR, which is calculated from the sum of squares for treatments. But this idea that we have treatments in this word, in SSTR and MSTR, mean square due to treatments, we're looking at between the treatments. And then down here, we're going to have mean square error. And we also have like standard error. And standard error earlier was telling us like, how far is some point, from another point, like from the mean, like our z-score, what's the standard error? And so we're looking at like 1 point's distance from another point. And so that's standard error. But here we have mean square error and within, and that's for the within treatments estimate of variance. So with the, mean square error, so this is like, mean square due to treatments, which is between the treatments, and then mean square error. And I'm just trying to clarify these terms here for you. So when you see them, you need to start thinking, is this like between the treatments, which is the MSTR, SSTR, or is this within the treatments, which is the MSE and SSE? And the way I remember that is that, right, standard error is like standard deviation, which is like the distance of 1 point from like the mean. It's the distance from 1 point to another point. That's standard error and standard deviation. And we've learned about standard error. And so mean square error is the distance of 1 point from another point within the treatment, right? We're really looking at like what is the variance within a treatment. And so we look at our data, we're looking at like what's the variance within this treatment. And the way ChatGPT presents the sum of square error is like 1 point from the mean of all the points in that treatment. So it's within the treatment. This is the simplified way to present it. But I'm just saying all that so that when you see SSTR, degrees of freedom for treatments, and SSE, degrees of freedom for error, right? You can remember your F statistic. You're going to have Mr. Mouse, I don't know. Another mnemonic device was coming to mind, which I don't think would have been appropriate. Mr. and Mrs., right? Mr. over Mrs., like that is not appropriate. Like total, we should all be equal. So Mr. Mouse, but you have the bigger one over the littler one, just in terms of letters, right? But you have up here, this one over that one. Now I'm gonna ask you, pause the video. There's a blower outside. Just looking to see how much of my sound's picking it up. I think we're all right. A little bit, picking it up a little bit. But I'm gonna ask you, I'm gonna pause the video till the blower. I'll ask you the question, then I'll pause the video. So, MSTR over MSE, Mr. Mouse, okay? That's your mnemonic device. Mr. Mouse, which one of these is between treatments and which one of these is within treatments? So pause the video and answer that. And that's what I want you to be able to do when you see like MSTR, SSTR, or MSE and SSE, right? I want you to know which one is between the treatments, right? It's like this is the mean of each treatment, the difference from that mean to the overall mean of all the data, which is between treatments, and which one is within treatments. So I was going to pause the video, but now the blower is quieting down, so let's keep going. The one that is between is MSTR, right? It's between the treatments, SSTR, MSTR, treatments, between treatments. error is within a treatment, right? What's the error with the variance within a treatment, or the standard deviation within a treatment? What's the variance, right? Within a treatment. So that's what I want you to be able to think about when you see treatments, SSTR, MSTR, that's between. And when you see MSE, SSE, that's within, all right? So then you calculate the F ratio, which is this, and they get that for an F ratio. And then they have their analysis of all that, and they put together their ANOVA table. So that is all going to be slightly different than what the book comes up with. So let's take a look at how the book does it, and then we'll come back and compare it to, the F value that was come up with in the MSTR, which is this, and the MSE, which is that. So MSE is 5.733, and MSTR is 258 MSTR. So here's how the book presents it. Here's their null hypothesis. And again, I don't think we need our little device, but we might as well because we're talking about it. So I'll just grab it, which is right. Is that it? No. I'll just have to go get it from back up here. It's right here. So we get our null hypothesis and bring it back down to here. And where does it go? That's the previous one. It goes right here. And we'll just move that all up. Go up. There we go. So we get our null hypothesis. Oop, that's too far. That has to all come down. And I missed some. That's good. Boom. All right. And once we get our null hypothesis, we have the level of significance is specified right there. And then we're going to compute the test statistics. So the mean squared due to treatment, so this is between the treatments, is X bar is equal to 73. And if we look up here to see what, ChatGPT got for X bar, X double bar, it's 73. And then SSTR, our formula for SSTR, so let's go get that formula for SSTR. And I think maybe I have it right here. So here's MSTR, and the numerator is the SSTR. So we have here our MSTR, and that's how we do the SSTR. And so it's going to be each mean minus the overall mean. You square it, and then you multiply it by the number of elements in each sample, right? So in each sample, we have 6 elements, and you could see that here. So there's 1, 2, 3, 4, 5, 6 in Atlanta, there's 6 in Dallas, and there's 6 in Seattle. But theoretically, we could have had like 6 in Atlanta, 8 in Dallas, and 9 in Seattle, right? And so those numbers would be different here. So we take the mean, that was that, 79, 74, 66. I'm just going to grab this actually and bring it over here. Come on. And I'm going to move all this up. Go on up. And I'm going to move it over. Go on up. And I'm going to paste this one in, and I'm going to bring it on down. Come on down. I'm sorry. I'm just keeping myself engaged. And can I squish that? I can't squish it anymore. And what can I do to make this fit? So I'm just going to move that aside for a second and see if I can move this over. And maybe that'll work. Just move it over to there. And this might work, ladies and gentlemen. And then bring this one on up. And oh man, it's so very close. And that needs to all come down just a touch. So I can't shrink that anymore. And I wonder if it could go this way at all. That's working. And now if I come over, did I make it? That's pretty good. All right. So then we have each of the sample means, 79, 74, what is that one? 66, 79, 74, 66. And we take that and minus the mean for all the data. And then we square it, and then we multiply it by n, which is the number of items. And that's how we calculate our SSTR, treatments, right? So this is between, and we're looking at between treatments. The mean of each treatment, I sound like Elmer Fudd there for a minute. The mean of each treatment, and how far it is from the overall mean of all of the data. So we get 516, and then we divide by 3 minus 1. And 3 minus 1 is our degrees of freedom, where K here is the number of treatments. And we subtract 1, and we divide by 1. And we get an MSTR of 258. So if we compare that with what ChatGPT came up with, they got 258 too. I like that. I like it when things reconcile and it's like it all checks and balances. But here we're doing another deal. So I'm going to move all this up so we have room because I like to see my data when I look at this stuff. And this is maybe part of what you're learning is just like, okay, I want to understand this. Let me get all my data and let me look at my data while I'm looking at this stuff. And here's the formula. Now I'm going to grab this table and Control C and put this table here so we can still see our data. Now we have the sum of square errors. So here's the mean square error, and the mean square errors is the sum of square errors. So there's the sum square of errors. This is how the textbook presents it. And it's divided by the degrees of freedom for, the errors. And I don't remember what that's called. So it's degrees of freedom for error. There we go, right? SSE. So that is going to be NT minus K, and NT minus K is 18. There's 18 total data values minus 3 different treatments. And so, okay, whatever, that's the formula. You just plug it in. You don't have to know how to engineer an entire BMW to use it. You don't have to know how to engineer this entire formula to use it. You just use it. All right, so that all makes sense, right? There's that, and then here to get this formula here, we've got 5 and 5 and 5. And so what that is like how many observations were in the sample? There were 6. Let's minus one of them. So 6 minus 1 is 5, so we get a 5 in front of each. Theoretically, this could have been like, 8 minus 1. This could have been like 9 minus 1. This could have been 6 minus 1 there, right? And then we multiply it by 34, 20, 32. 34, 20, 32. We multiply it by the variance for each of those treatments, okay? The sample variance for each of those treatments. And so there you can see that happening, and then you add all that up, you get 430, and then that's your SSE, sum of square errors, and then you get your mean square error, and I'm just checking to make sure I'm using the right terminology, mean square for error, and you get that by dividing the SSE by your degrees of freedom for SSE, and you get 28.667. And then to get your F statistic, Mr. Mouse, put your MSTR, that's your between treatments, over your MSE, that's your variation within treatments, and you divide those two and you get 15. Okay, so that all is cool, but when you look at this, we got 430 for SSE, and we have 15 and 28.67 for MSE, and ChatGPT came up with something totally different. So their mean square is 5.73, and our mean square is 28.667. And we have 430 for our SSE, and sum of squares, that's it right there. They got 86. So they got really different numbers, and that's because they use this formula here. And I'm like, okay, it's a different formula. I asked ChatGPT why that difference, and this is what ChatGPT came up with, right? So here I dropped in the PowerPoint presentation. I gave it this description. And basically what it said is it seems to be an error or a simplified approximation, whereas 430 is the correct and more reliable calculation. You should use the 430 SSE value from the original presentation for any further analysis, right? And so I'm not sure why ChatGPT forwarded this more simplified formula, if that's something that's actually done in statistics, or it's just one of the small times where ChatGPT makes a little bit of a miscalculation. But this just illustrates, one, you got to think for yourself, and then you just got to get in there and really kind of tear things apart and try to understand them and notice the differences. And so that SSE, what's interesting about that is if we go back up here and we look at the previous problem that we did, and in the previous problem, and I think I put this into the notes, and it'll be easier for me just to click here on the notes, and I just got to find right here, and oh, I never clicked to see explanation there. We'll see where this takes us. And so here in the previous one, which is for the Chem Tech, which was the assembly times, and it's for the experimental design as opposed to observational study, experimental study as opposed to observational study, right? But in that one, and let me just get back there, and so to get there, I need to click on, I think, is it this one? Is it this one? I need to click on this to get back there, right? But in that one, ChatGPT and the textbook came up with the same value. So I'm going to find that and show it to you. Okay, so here it is, and so F9.18 is what ChatGPT came up with, and F9.18 is what the textbook has. And then also ChatGPT has 260 and 28.33, and here it's 260 and 28.33. I love that they reconciled. But even in this one, you know, ChatGPT was talking about doing your sum of square errors with this formula here. So sum of square treatments, let me find, oh, here it is, right? Which is the exact same formula. And so even though it talked about doing it with that formula, it got the same result that the textbook got. And the textbook was talking about doing it with this formula here. And that formula there is, let me find it, hold on. All right, here's the formula, MSE. The formula for SSE is this one in the numerator, right? That's the numerator. And so on that one here, right, if we just paste that formula here, this is the formula that, you know, the textbook used. And that's for getting the sum of square errors right here, where they were saying, all right, we're going to take 4, and we had 5, you know, items, observations in each treatment. So we're going to take, for each one, 5 minus 1 is going to be 4, and then we're going to multiply that by the variance, 62, 66, 52. And here we have, oh, sorry, the variance, that's the mean. I'm like, wait a second, 31, 26.5, and 27.5. And so even though in the previous one they got the same result, might be interesting just to parse that a little bit more and actually run the math for, you know, the formula that was forwarded by ChatGPT. But they got the same result in the previous one, and in this one they got different results. So anyhow, that's kind of interesting. You just got to stay sharp, stay on point, and investigate, and have that spirit of adventure and exploration, and do your calculations. And so we have a difference, a discrepancy between, you know, the book, the formula that was provided by the book, and the formula that's provided by ChatGPT. And the explanation that ChatGPT gave was maybe the one that was given earlier was just too cursory, and the textbook one is more thorough, but this is the one we should go with. There's a great quote, when the book and the bird differ, believe the bird. And that's from James Audubon. When the bird and the book disagree, always believe the bird. And James Audubon was the founder of the Audubon Society, and a super interesting story. I'll tell you about that. And to tell you about that, I'll tell you about it at the end of this video. But cool. I think I'm not totally sure if it's the Audubon story, so we'll check that. All right, so there's calculating our F statistic, and then here is our ANOVA table, right? And with that information there, we could go up and we could draw this. And so here is our F statistic, 15, right? We have 15, and then we have this at a 0.05 level of significance. And if we look up our F table, so let me find our F table, just one second. And I haven't downloaded it, so I gotta go get it. I'll be right back. Okay, I just got our F tables. Whoops, that's not what I want to move. I wonder if that messed up your recording. That should be okay. Hopefully that's all right. Maybe you saw that. Did this get moved, or is that just, I think that's fine. All right, it looks like it's recording. Okay, so here are our F tables, and so there's the one on the left, gives you the probability distribution, and here's the one on the right. And I'm just going to bring these down over here. And so if we look up 0.05 and our degrees of freedom for treatments, which is the numerator, right? And treatments are between, you can see the notation there. So we have 2 degrees of freedom in the numerator, and degrees of freedom for the denominator. This is the denominator, it's the within, it's the DF for error, and that's going to be 15. And so with 2 in the numerator, here's the degrees of freedom in the denominator, and here's in the numerator right there. So denominator, we need 15. This only goes to 5, so I'm just going to close that one. And the other one, which is right here, This one does go to 15, and it's at 2. And at 0.05 in the tail, our F value is 3.68. And so here we have 0.05 in the tail, and our F value is 3.68. The one we calculated is 15. So if we look at this table here and we say, okay, what's 15? And let me just see if I could like move this over like this. Windows. I'm sure there's, main Windows. I'm sure there's some way to turn that off. And I don't want to take the time to go figure it out. I'm not sure why it doesn't just make that bigger and then I can't crop in on it. But anyhow, so with our F statistic of 15, if you look at like here, because we're at denominator degrees of freedom 15, numerator degrees of freedom 2. So here's that, and we're at these numbers here. We have 2, 3, 4, 6. 15 is going to be way out here. So it's going to be between 0.01 and 0. Right? So that's what I put right there for the probability value, the p-value, the amount of probability that's from this point to the right in the tail. And so both of these, whether we use the critical value approach with the F value or the p-value approach, both of those criteria tell us to reject the null hypothesis, and at least one of the population means is different. So that's what we calculate after doing all this and getting our table. Okay, there's 3 last slides here the textbook has, and here is how they set all that up and talk about it. And so here is the p-value approach, and so they reject, and you can pause the video and read about it. And here's the critical value approach, and they reject, so you can pause the video and read about it. And then the way they talk about it is we can conclude that the mean examination scores of employees working at different plants is not the same, right? Like they use a lot of double negatives and things like that. They have different scores at the plants, like they have different populations. And so we're looking at something where the sample means in helping us determine and make inferences about the population means, right? They are not the same. They are not, all the means are not equal. That's the null hypothesis. They're not the same probability distribution. These samples are not pointing towards the same probability mean. The samples are pointing towards different population means. Different population means. It's not the same population mean. They're pointing towards different population means. The sample means are pointing towards different population means with different probability distributions. So that's the conclusion of that. So that's another example of using ANOVA, and that's using ANOVA for an observational experiment, an observational study, as opposed to an experimental study. And the experimental study was the one right before that. I hope that's helpful for you. I think it just really reiterates, the importance of, like, ChatGPT can be super helpful, but at the same time, you got to take it with a little bit of a grain of salt, and you got to check it because it can help you learn because it makes you think and it makes you like compare different material and ask yourself questions. So that's really useful about it. But it's also good to know that you need to be doing that check-in and checking things out. All right, that's this. Now in the next video, we got a little bit more to cover, and then we have actually one more presentation after this one to go through. So we got some more to go through still with this module. See you in the next videos.